Welcome back, everyone. Module 13, day 3, model selection and multi-class classification. A little redundant, I guess. Um, all right, today we're going to be applying the model fit predict process on classification models with multi-class data sets. We'll get into what that means later. And we're also going to analyze and explain the results when training multiple models on the same data set, comparing which model performs best. And I'll actually do that one first. And we're going to do like a mini project tonight, similar to last Thursday. But first, we'll do a little bit of warm up. All right. Just to refresh everyone's memory, we're going to talk about preprocessing data, training, and evaluating multiple classification models on the same data set. All right. All right, so let's look at some code. Um, so this data set is about tic-tac-toe, and basically given a variety of setups, and we see here the top left square, the top middle square, and so on, and then the class as to whether this was a positive or negative setup. All right, so let's include our libraries, and we got a lot of libraries. We have a lot of libraries because we're going to be looking at this data set with multiple models and see how the multiple models compare. All right, so let's bring in our spreadsheet. And as you can see, there's a column for each of the 9 positions in tic-tac-toe, and whether it's an X or an O, or blank, B for blank. And the class has to say whether it's, a positive or negative outcome based on that setup. All right. So we look at DF types, we can see that everything's an object. Everything's a string. That means we have to do some preprocessing. All right. The target variable, which is basically positive or negative, we can use label encoder on that, and that should be fine. So y equals label encoder dot fit transform of df class, right? So just doing that all in one line. Um, you could extend it out if you wanted to, but there's ways to combine all these things. You get it all in one line. And when we run that, you see you get an array, right, of ones for positive outcomes and zeros for negative outcomes. And looks like there's a lot of data. So let's take a look quickly how big that data is. Yeah, 1,000 rows. Okay, we need to get the features, which is everything except class, which was the outcome. So boom. And I'm going to do our train test split. Okay. Um, the outcomes, I'm sorry, the features can have 3 different values, X, O, or B. So label encoder is not a good candidate. We need one hot encoder. So we'll use one hot encoder. If we get an unknown value, we'll ignore it. Sparse output is false. The D type is int, so we're gonna give us an integer. And then our X train encoded will be PD data frame data equals one hot encoder dot fit transform of X train and the columns will be, one hot encoder dot get feature names out. Again, this is just a way to do it all in one line. We previously did this in multiple lines. Um, and we look at X-train encoded, we could see that you now have 3 times as many columns as we did before. We had 1 column per square before, so 9 columns, but now we have 27 columns. So like top left square blank, top left square O, top left square X, and it's 1 if it's true and 0 if it's false. All right, so all nice and encoded with 1 hot encoder. And now we're going to model this and fit it to a logistic regression classifier.
Hey,
Uh,
Professor,
yeah,
the B is blank, right?
yeah, yeah,
Okay, and then the outcome is if X wins or
yeah.
okay, and if it's one if X wins and zero if X loses or if the O's wins, right?
Or if it's a tie, yeah.
Or it could be a how is a tie classified? Everything else,
It's
right?
just the yeah, it's either a positive or negative outcome. So it's just got 2 values for class.
Okay, so it's positive or one if X wins and it's zero, the class is zero. If the O's wins or it's a tie, right?
I have value counts. Um, let's try that. There we go. So we have 626 positive results and 332 negative results. So there's no tie in this. In tic-tac-toe, you can have ties because you have like a no-win scenario. But here it just describes whether these are positive or negative outcomes based on the layouts
Oh, okay. Why would X win about two-thirds of the time?
because it gets to go first.
Okay, right.
Um, Also, this is just based on the data that's given. We only have 1,000 rows. That might not be all the possible scenarios. There
Okay,
might be more,
all right.
right? I haven't actually done the math as to say how many total scenarios there should be. Um, I would suspect it's more than 1,000.
Okay, all right. Thanks.
Mhm. Okay, let's use a logistic regression classifier. All right, so we load our model, logistic regression, and gonna fit it to the X-train encoded. Very good. And now we'll print out the accuracy for this model using the .score function, passing in the the encoded X and Y. All right, so obviously the training data is often more accurate than the test data because that's what it was trained on. And it doesn't know about the exceptions that exist in the test data. But the test data is the more legit score here. So we want to pay attention to the test accuracy. And with logistic regression, we got 0.975. Great. So let's try SVM. So we load a model, it's support vector classifier, SVC, kernel equals linear, and fit it and score it. Again, 0.975. So SVM and logistic regression are scoring about the same, almost exactly the same. And that may be due to like the nature of how simple this problem is. Now, let's go to a k-nearest neighbors model. So we'll do a KNN model with neighbors equals 5. We're not going to go into like, hey, what's the best value of K in this scenario? We're just going to pick 5 out of the blue. Obviously, when you're using K nearest neighbors, you do want to play with that value of K from time to time.
Hey Sean,
Uh,
quick question. Don't we have to choose two neighbors because there are only two options? So either it'll go to one, it'll be close to one or the other.
no, no, there's 1,000
Okay.
data points,
Okay.
750 data points after you do a train test split, right? So in a training data set with 750 data points, you get a new data point and you're going to be near some of those, right?
Mm-hmm.
Some of them will be in class 1 and some will be in class 0. The outcomes are only two choices, but the data rows themselves, the rows of data, there's a lot of those.
Okay. Okay. So I thought neighbors is like the number of outcomes.
No, no, no. Um, if you plot all of your observations, right,
Uh-huh.
those are your neighbors. And if you get a new data point in, it's going to look at which observations are closest to it by measuring distance in the dimensions, in the features.
Okay.
So even though this one has 27 dimensions, we can still determine, which individual row is closest to this one, or in this case, which 5 are closest. Best 3 out of 5 determines, the outcome of the new dot.
Mm.
All right,
Okay.
and then we do the test accuracy. We get 0.942, not as good as logistic regression and SEC. But look how easy it is to like add another model. All right, let's add a fourth one. We'll make a decision tree classifier and we'll fit it. And spit out accuracy for the decision classifier. You can see the training data models perfectly, as decision trees like to do, but the test accuracy is only 0.933. And then we go to our favorite classifier, random forest. And for this one, we're passing a parameter of 128 estimators. That might be a bit much since there's only 1,000 points of data. And we'll fit the data and run it. And because you have 128 estimators, yeah, surprise, surprise, you have one perfect accuracy. But interestingly enough, this really isn't that badly overfitted. The test accuracy is 0.992, the best result of all 5 models.
Sean, I'm sorry, what was this 128?
Number of estimators
What was that?
in the random forest classifier is like how many decisions it's going to allow it to have in its tree, and all of the trees total. So if you remember the chart that showed all of the decisions that were in the
Yeah.
decision tree, each one of those is one decision. Um, in
So why
random
did
for
we choose 128?
Well, why did we choose 128? I didn't personally like the 128. I thought it was a little high. Um, the number that you pick is going to be a trade-off between being underfitted and overfitted and computation cost. This one computed in under a second, so computation cost is not a factor. So 128 is a lot compared to the total data set of only 750 in the training data. So that's, I was a little concerned, but the test accuracy score came out very well. So it turns out 128 was okay.
Professor, how do we determine what number we should use for our estimators?
Exactly.
Well, it should be less than the number of elements in your training data set, right? because if you have equal to or more estimators that are in your training data set, then it's basically going to say, hey, is it this one? Then true. Okay. Estimator number two will say, well, is it row two? And if that's so, it's true, and so on. It'll just basically get one estimator for every single data point, and that's not really a model anymore.
But we have
So,
1,000.
yeah.
We have 1,000. How does that correlate to the 128?
So we have 1,000 points. We have 750 in the training data set because of the train test split. So we should have less than 750 in the total number of estimators. If you approach 750, you're really going to be getting extremely overfit. So you want to be much less than the total number in the data set.
Is
So
there
128 is a lot less than 750, right? It's like a fourth, but I still think it's kind of a lot. You know, the trade-off is the more estimators you have, you know, the better its prediction power is going to be up until a point where it starts overfitting, and then the test accuracy will start to drop off. So if you really want to be picky about it, you can actually try multiple values of number of estimators and see which one gives you a better test accuracy.
so basically what we're to do is to, after we've done the perform the train test split the first time, and that after we once we've done that, we should basically go lower than whatever is the new number of rows, and try our best not to come close to that. Like, I'm I'm trying to find the rule of thumb
Yeah.
for how many estimators.
Yeah. So here it looked like it was about 1/4 the size of the training data. You know, which is probably, I guess, a decent guess. Sometimes even that number is too high.
So no more than a quarter of the size.
Yeah, I mean,
You would
basically what
say.
you can do is you can run it multiple times and see which one gives you a better test accuracy. Because if you plot your test accuracies against your number of estimators, you will see that at the low number of estimators, the accuracy is low because the model is not very smart. And as you add more estimators, it starts to go up, right? Because it's got more and more decisions it can make. After a while, though, it will peak and start to go down again because now it's not predicting the model so much as it is predicting exactly what the training data looks like, as opposed to what the model means in general.
Got it. Okay.
Right? And if you have almost as many estimators as there are points in the training data, then it's basically what it's doing is it's predicting exactly the training data and not the model.
Got it.
So
Okay.
typically, there's an underlying phenomenon that's in your data, right? Like some random type of function that you don't know that describes the behavior of the data. And you want a model that mimics that. You don't want a model that just echoes what the training data says. Because then your test data comes in and it's not going to be accurate at all because all your model knows is how to spit out answers if you exactly match the training data. Well, what happens if you get a new data point that's not exactly the training data? Well, then you need something that's kind of reflecting, you know, the model of, you know, what's really going on.
Professor, can you just repeat again? You said that the for the random forest classifier, the 0.992 accuracy, you mentioned that that was not overly fitted. Can you explain the
It's
logic?
the test accuracy in 992 is really good. I mean, it's less than the training accuracy of 1.0, but 992 is better than the 933, the 942, the 975, and the other 975. So the other four models had lower accuracy scores than Random Forest.
Okay.
So I would say, yeah, 992 is great.
For the KNN model, could you just change the n neighbors to 10 and see what happens?
Yeah. Made it a little bit better.
Yeah, but still not as good as the random forest. Yeah.
Mhm.
And also neighbors should be even, right? Oh, sorry, odd.
Yeah, ideally it should be an odd number.
Oh, 11. Yeah. Okay. Is there not to beat the dead horse, but is there a reason why in this case the random forest classifier provides the best accuracy?
The
Or
random,
another, or
yeah,
not, or
it's
another way to ask the question is, we have to choose, from our tool set, which model to use.
mhm.
So are there certain cases where one model is better, or do you just have to,
Yeah,
um,
when your data looks linear,
mhm,
then the earlier models are going to be better. Um, this is a tic-tac-toe problem. What part of tic-tac-toe looks linear,
Yeah.
right? If the x's are I mean your x's, o's, and that you basically have true falses for the 27 columns. There's no linearity to it, right?
Mhm.
It's not like, hey, as this feature increases, my outcome increases. I just don't get that here, right?
Right.
Um, you can have zeros over here, but have three x's in a row over here, and then that's a good outcome. So, it's nonlinear. And when you're nonlinear, models that are based on linear are not going to work so great. So logistic regression's not going to work, SVM's not going to work. K nearest neighbors may work just because two tic-tac-toe layouts that look similar may have a similar outcome. If it's like just off by one square, right?
Mhm.
But then again, in tic-tac-toe, one square can be the difference between a win and a loss.
Okay.
So
So just a recap of the five models, the first two are linear and the last three are more non-linear.
right.
Okay. All right, thanks.
So random forest is like decision tree, but what it is, it's like it's a bunch of weak decision trees that combine together to create an overall smarter outcome. Random forest is more like thinking, right? Because it's like if you see this kind of pattern, you might be winning. If you see that kind of pattern, you might be losing. Combines all this stuff together and generates an outcome. And that's why random forests seem to be doing better in this case, because there's a lot of like commonalities in tic-tac-toe.
Okay, all right, thank you.
Similar thing is would happen if you tried to model chess with this.
I still don't understand this 128. How out of from 1 to what was that 725? Why we chose 128?
Why not? You have to
Then
pick a
why?
number
Why
between
not
one.
127? Do we pick a random number?
Yeah.
325, 478, and we
I
just
mean,
try?
you could try like 1/4, but I personally think 1/4 might be a little high, but if you want to play with it, you try different numbers. There's nothing magical about 128 here. I don't know why they picked 128. They just did. Okay. But there is an analysis you can do where you try different number of estimators and see how it performs. And if you can't do that because the data set's too big, you can take a subset of the data and try different estimators on the subset of the data and see, okay, how does this work on my subset? And then get a better handle for like what percentage of the training data seems good, and then move that over to like doing your whole data. Then again, on very, very large data sets, you can't do, say you have 1 million rows, then you don't want to have 250,000 estimators. It might take forever to compute.
And Sean, as far as the estimators are concerned, rule of thumb, it doesn't matter how many features there are. So it's just based on the number of rows.
Yeah. Well, let's see. If there was only one feature, yeah, no, even if there was only one feature, it would still be based on the number of rows because it's nonlinear, right? I mean, if it was linear, then you'd only need one estimator, to figure it out, right? If there was one feature and it was linear, then all you need to know is like, hey, if X is less than 5, it's a yes, and otherwise it's a no, right? And you'd have the whole thing solved in just one estimator. But in nonlinear data, it could be yes for a while, and then no for a while, and then yes for a while, and then no for a while, and then yes for a while, and no for a while. Um, and in that case, yeah, even if you had one feature, you might need several estimators to like get a more accurate model.
Thank you.
Hey, Sean, quick question. For the one hot encoder, should we not encode it before print test split, just like we did for the label encoder?
No, you can't you can't put the encoding of the features before the train test split. No, no, no.
Okay. So feature encoding always after train test split, but the Y encoding before, right? Because we did the Y encoding before, like through the label encoder.
Yeah.
Is
Yeah. I mean,
that
typically
is
you would
that
do
kind of
your
the rule?
Y encoding afterwards, but in this case, it's not that important because the the Y is just 2 classes, yes or no, and it's always going to be a yes or no. Um,
Yeah, but same
Ideally,
standard
you
goes
would do the
for
Y
feature
encoding
control.
after the train test split as well. Yes. Otherwise, you get data bleed, and you don't want data bleed because then your models could be less accurate.
Mhm.
If if the model which is running on train X train and X and Y train, right, knows anything about X test and Y test, that doesn't reflect reality, right? Because in the real world, when you get new data points, your model doesn't know anything about those data points. But if the way you trained it was in such a way that it did know something about the test data, then your test accuracy is going to be lower than your real world accuracy.
Okay.
Wow. Okay. We have a lot more questions on that than I expected. Um, all right. All right. Moving on. So okay, so when we compare the 5 models, um, we got various results, right? And the random forest gave us our best test accuracy. Um, and whenever we see a training accuracy of 1.0, we are a little suspicious. And typically, if we see a training accuracy that is perfect or near perfect, we suspect it might be overfitted. Just something to be cautious about. Typically, though, when things are overfitted, the training accuracy will be higher than the test accuracy. And here, in the decision tree, it looked like it was definitely overfitted because training accuracy was 1.0, but the test accuracy was among the worst of the 5. Now here, the training accuracy was 1.0, again, suspicious, but the test accuracy was 0.992, best of the 5. So we'll take it. All right. The other gotcha of this problem was that there were more scenarios where X wins than O wins in our data set. And that leads to something called an imbalanced data set. So we'll talk a little bit more about that later. Okay, so let's do that. We had the best accuracy, the model, okay. And now we're going to talk about car acceptability. All right, so that is going to be another data set we're going to look at. All right, so let's pop out of there and go over to exercise 2. All right, so for this one, we're going to have like a car evaluation database. And it's got things like various attributes like buying the car, maintenance of the car, the doors, the persons, the safety features, lug boot, which I guess is the size of the trunk. All right, so we load in our data sets and load in our data, and let's take a look. And we don't have that many columns right now, so that's not too bad. And then the class we see is either this is an unacceptable car or an acceptable car, right? So if we do value counts, we actually see 4 options for our outcome. And that's new for us because previously we only had 2 values for y, and here we have 4. All right. So the outcomes could be unacceptable, acceptable, good, or very good. And then we also see that the others have like a variety of values as well. So we d-types and we say, yep, they're objects. We'll go ahead and map that to y. And we'll say x is going to be everything else. And now we'll do our train test split. And we can use label encoder. So we're going to use label encoder on y. And we'll basically say label encoder fit transform on Y train. So we're going to build the label encoder on the Y train data and make Y train encoded. And then we'll do Y test encoded using the same label encoder that was built on Y train. So it was fit on Y train, but transform is going to be saying we're going to transform Y test. So make note that the first one here is fit and transform. So it's actually fitting and transforming it's fitting using Y-train and then transforming Y-train's data. The second one is not fitting to Y-test. It's already, the model's already been fit. We're just transforming Y-test. Okay. And we see a variety of outcomes from 0 to 3.
Professor, can you explain that again? You're doing both on Y train, but just one on Y test?
Yeah, when you build an encoder, you fit it on the training data. And then you transform your train and test data to get your new encoded data.
Okay. Yeah, I think we did that before, right? That was the
Right.
pattern. Okay.
Yeah. The only difference here is like they have a function that does fit and transform together in one shot.
Okay.
Yeah.
So
I just don't want you to like blur over this and think that this function and this function are the same. They're different.
okay,
Right.
so before we did the fit and then the transform, but we always did the transform for the Y test. When we encode it, we always did the transform just on the Y test, and there's no fitting on the Y test, right?
Yeah, you fit to the training data,
Okay.
right? Just like we're building our model on the training data, we build our encoders on the training data because the encoders shouldn't know anything about the test data. If the
Okay.
encoders know something about the test data, that's information bleed, which means you're going to get a weaker model at the end.
Okay. Thank you.
All right. For X-train data, for those columns, we're going to use one hot encoder. There's a variety of different options for each, right? So there's several options for buying, several options for maintenance. Doors and persons are numbers, so it's not going to encode those, but lug boot and safety will get encoded, right? So one hot encoder will take care of that. Again, we see this fit transform on X train, but when it does X test encoded, it just does the transform. So this line loads the encoder. This line fits the encoder and transforms the training data. And then this line transforms the test data. Oh, and since doors and persons, I guess, were strings, they go ahead and applied one hot encoder to them. Okay. Were they strings? Yes, they were strings. So that's interesting. So doors and persons look like they're numbers here, but when we did D types, we saw that doors and persons were objects, which means they're strings. And therefore, one hot encoder will treat them as strings and make a column for each one. So doors 2, doors 3, doors 4, doors 5 more, and so on. I guess it's because it's possible that in some rows, the value for doors is 5 more. And then the value for persons can be more. All right.
Shouldn't we scale this data, Sean? Rather
Well, at
than
this,
converting. Yeah.
yeah, you don't need to scale it because it's just zeros and ones.
No, I mean the doors and persons. If we can convert it to a number and scale it, wouldn't that be
No, we
better?
can't convert it to a number, and here's why. Here, let me just add a box here. So df doors value counts. All right, so we have options for doors 2, 3, 4, and 5 more.
Got you.
See, string. Can't
But
can't scale that.
can we cast 5 more to like something like just 5 and then scale it?
Yes, if you feel that's acceptable,
Okay.
you know,
Because
then your 11-door car will be treated as a 5-door car.
yeah, but over here in this it's the same value, whether it's 5, 6, 7, 8, everything is same value. So should
Yes,
be
but it's
acceptable.
not it's not giving it a linear relationship.
I see.
You know, it's treating these as 4 completely separate classes.
Hmm.
It's not saying that, hey, 4 doors is twice as good as 2 doors or anything like that.
Yeah, the data looks a little bit suspicious. Everything is 432. And what can be a 3-door car? driver door, passenger door, and a trunk. Is that a door? A trunk door or a hatchback?
Yeah, like an SUV or an AMC Gremlin or anything with a hatchback.
Yeah. Okay.
I was more concerned about the 5 doors.
5 doors,
Yeah, I've never seen a car with 5 doors.
a Mazda CX-5, Toyota RAV4. Just
Really?
about every car on the road today is 5 door.
Really? Interesting.
Get out more.
Okay, so the back door would be considered a door, but yeah,
If you can crawl in it, it's a door.
okay. And then the four door would be something that doesn't have the trunk door in the back. Right?
Yeah,
Yeah.
like a sedan. Remember sedans? When was the last time you actually saw a sedan on the road?
Yeah. Okay.
What's sparse output? It's on the one hot encoder line. It says sparse output false.
Yeah. That I don't have that off the top of my head. Let's fire up this puppy. What does sparse output mean on one hot encoder? Okay, so a memory efficient representation that only stores non-zero entries. And sparse output is false, saying that the zeros will actually be stored as the number 0. This is more of a technical thing for how things are stored in memory. But since our models kind of want how you use NumPy arrays, most of the time we'll use sparse output equals false. The true is the default. And we get really, really large data sets where one class is very common, and that'll be the one hot encoder will say that's going to be the default, where I'm just going to leave it blank and only apply values to the other cases.
Got
And
it.
so you'll see a bunch of data where it's just a bunch of like nulls for the most common case.
Okay.
Okay. All right, so we did one hot encoder. We talked about doors, and then there was persons, and we'll probably see that if I applied this to person, is it person or persons? Persons. Is it the plural of persons, people? So if it's a 2-person car, a 4-person car, or a more person car, again, we can't use a X scalar. We can't use a standard scalar on that because more is not an integer. All right, so now everything's been turned into ones and zeros. And we can encode our test data and fit it to a logistic regression and look at the accuracy for logistic regression. 917, all right. And let's compare it to a support vector machine. 977, much better with the SVM than logistic regression. Okay, so that's an instance where these two behave a lot different. Fitting it to a k-nearest neighbors model.
Hey Sean, I have a question.
Yeah.
In SVC model, we chose to use kernelless poly. Was there an easier way to identify like, well, this is not linear data, and hence let's go with poly?
It's definitely not linear data.
Right.
Anything
But,
about this
but
look linear to you?
no, I mean, but with tic-tac-toe we used linear, right? That wasn't linear either. But I'm just trying to understand like what's the rationale behind just picking linear there versus poly here versus like
Yeah, I mean, when you have nonlinear data, you don't want to use the linear kernel. Poly is better.
right.
So they probably should have used poly on that previous exercise.
Okay. So
Good.
basically, if it is not linear, we just the alternative is poly, right? Obviously, radial also should be something that we would it'll be easy to determine, I would say, right?
Yeah. I mean, there are other kernels available for support vector machines. And again, this is something you can play with, when you're trying to tune your model to get the best results.
Got you.
But some data just does not have a linear relationship. It's not like things get better if this dimension goes higher. You know what I mean?
Mm-hmm.
In here, all of our dimensions are only true or 0 or 1. So
Okay.
it's even surprising that poly worked, but it did pretty well, actually. We got a 0.977 on the test accuracy. All right, k-nearest neighbors got a 0.919, so did not perform as well as SVM. Again, a little surprising. And that's based on nearest neighbors being 9. Don't ask me why they chose 9, right? Obviously, someone did the analysis and compared different values for neighbors and figured out that 9 was probably best. Decision tree. All right. Again, decision tree likes to go really strong on training data, but not as strong on test. And then random forest. We like random forest. Let's see how it performs this time. And it looks like it overfitted. Again, they chose 128 estimators and came out with 0.961 on the test accuracy. Kind of curious. If they dropped it down to 64, would that actually be better or worse? Actually got better by reducing the number of estimators. Well, look, so it's something that you play with, right? Okay. And so we looked at these and we see that the SVM seems to be the winner on this one. And it say, hey, did any of these perform too well and raise suspicion? Right? And both the decision tree and the random forest trained to 1.0 to perfection, which is always suspicious, meaning that they were likely overfitted. And that showed up when their test accuracy was less than the training accuracy. Still pretty good. 0.96 is nothing to scoff at, especially since it was better than k-nearest neighbors and better than logistic regression. It's just SVM happened to outperform it this time. Okay. Right, so now we are definitely a little behind. Not too far behind. Okay, good. All right, so we're okay. So we got that. Talk about mini projects. So tonight we're going to break up into mini projects, and let's take a look at the README. So if you go to exercise 3 and look at the README, you're going to have a variety of different data sets to choose from. All right, so when you go into your groups, first thing we want to do is explore data sets and then do some data pre-processing, right? Figuring out, like, do I need to get rid of nulls? Do I need to transform any of my data? Do I need to do one-hot encoder? Do whatever pre-processing you need to do. And then, so we'll do 25 minutes on that, and then we'll do the break. And then after the break, we will do model training. And during model training, that's where you're going to be trying to run your data on a variety of models to figure out, like, which models you like the best and tweaking some of the parameters. As you get your group together in groups, you're going to have 5 problems to choose from. So 2 of them are binary classification data sets, which is like the stuff we did on Monday and Tuesday. And 3 of them are multi-class classification data sets, which is more like the one we just did. Doesn't matter which one you choose, just get together as a group and pick one and download the data, do and explore it and figure out how you're going to do pre-processing on it. All right. Okay, so we'll go to breakout rooms. We'll do 25 minutes on exploring the data, pre-processing, and then after 25 minutes, we will call for a break. And then after that, we will go back to breakout rooms and continue with model training.
Hey, Sean, we have 21 students today. Do you want to do 5 breakout rooms or
Where
still?
is everybody? Yeah, let's do 5.
Okay.
And every team gets to choose which model, so don't worry about what the other teams are choosing.
Should be good.
What I like about these is they're good warm-ups for the real project that's coming in a few weeks. That's where you have to get your own data and then do your own analysis, and you have no idea if you have a good data set or not. But at least you get to pick data that's, like, really relevant to you. Okay. Let's spend a few minutes talking about your experiences. Let's start with the team from room 1, Carl, Misha, Dwani, and Vinyak. Did you face any issues or problems on your data processing?
Well, I think we did pretty good with the processing because we realized when we imported the data and looked at it and looked at our D types, we saw that the class, which we had to work as Y, was a object. So we knew we had to use something to transform that from an object. And then right from there, we were really trying to remember whether we do, like the encoder before the test train split, but we figured it out. And then we first decided to run linear regression on it, and we were able to run linear regression, random forest, SVM. We realized maybe it was a little more complicated, so we went into gradient boosting model and then tried the k-nearest neighbors as well. And then when we looked and compared all the data together, we noticed that our SVM model and the gradient boost were the ones with the most accuracy in the testing. But we decided that the gradient boosting classifier was better because because their test scores were exactly the same. And so we compared, we chose the gradient boosting classifier because the training score was better on
Okay.
there than it was on the SVC or SVM model.
Gradient boost is one of those models that a lot of people reach to these days. You know, random forest is always a good one to start with, because it's a great general purpose model. But sometimes, I mean, often people find that they're getting better results with gradient boosting. Okay.
Yeah, Professor, just we picked the last one, which was the orthopedic one, the bone. And it looked like from the 6 or 7 columns that it should have a more of a linear relationship. So I would think that so can you just remind me the gradient booster, that's non-linear? Or
Gradient boost is more linear, yeah.
oh, it's more linear.
It kind of like, well, let me see. Gradient boost.
Yeah, because it had measurements of bones or width or something. So you would think that the relationship
No, I think gradient boost is like random forest, but it's boosting the weak learners and penalizing, I mean, boosting the good learners and penalizing the bad learners is what it's doing.
yeah, but I would thought the linear regression would give the best result, which is kind of strange. But
Yeah.
anyway, okay, thanks.
Well, just because something appears to have a linear relationship doesn't mean that relationship's actually linear. Sometimes, although things increase as, sometimes you get like more y as you increase x, but that might be like a geometric progression or an exponential progression. Or you may get data that actually like y starts low, goes high, and then goes low again. That's another scenario that happens sometimes. And you can't always visualize that by glancing at the data unless you do some charts.
Okay,
Uh,
all right,
um,
that would make sense. Yeah. So the severity of the problem with the bones might be at a certain length or width or something. Yeah. So it wouldn't be linear. Yeah. Okay.
right.
Makes sense. Thank you.
All right. Let's hear from group 2. Avenate, Thomas, William, Giannis.
Yeah, we did a couple of those. We did the churn data and the letter data, just try a couple of different data sets, and did most of the models that we've seen in the exercises, and found that actually the best one, I think, in both was the extremely random trees classifier. Although we were getting in the churn data values on the training score close to 1, and then actually a value of 1 for the letter data set.
Did you have any challenges with your code?
Not really. We ran like the K, tried the loop to find out what the best value for K was for KNN, the KNN model. In both cases, just referred to some of the examples we worked on this one, so that was fine. Yeah, no real issues.
Okay. All right. Let's hear from room 3. Omar, Sami, Letitia, Jean-Luc.
Hey, so we did the analysis on the phishing data. We noticed that the data was pretty much split as like 1, 0, -1, and each one meaning legit. So on the phishing data, it was like 1 was legitimate, 0 was suspicious, -1 is phishing. And so what we realized is that we had to encode pretty much all the data. So not only the result, which was yes, it's fish 0 or 1, which was phishing or non-phishing, but also all the features as well, because we couldn't really use the numbers. They were basically classes. So it was either phishing, non-phishing, and the others. So we encoded both the X and the Y data, fitted amongst all the models that we pretty much learned, since it's a pretty simple process. And we found that the decision tree classifier had the highest testing accuracy. All of them pretty much ranged around from like 80 to 85%, and for the testing accuracy, and the decision tree one had the highest at like 87%.
Okay. Interesting. Don't often see decision tree winning these contests.
Yeah, it was pretty surprising.
Did you have any difficulties with your code? Any interesting challenges?
Not really. I was trying to start the pipeline process, but I guess trying to figure out how, because we encoded the Y data with label encoder and the X data with um the one hot encoder. So I kind of got
Mhm.
confused at how to, in the pipeline, separate the steps as you know, on the Y data I specifically wanted this encoder, and the X data I wanted the other encoder. So I instead tried doing it with the like just making another function to encode the data instead of using some of that part of the pipeline. So
Okay.
it was only the pipeline stuff that was a little confusing.
Yeah, pipelines are just ways to automate putting the models together when you have like several spreadsheets to go through and you want to
Right.
analyze them separately.
I see.
All right. Um, all right, let's see. Let's hear from room 4, CJ, Ryan, Robert, Tamara.
Yeah, I'll go. We analyzed the churn data set. We went through all 5 models. The best one we got was K-nearest neighbors 3 kernels. But like at the end, I guess the trees in the forest, they had the same exact training score, but the test scores were a bit different. And we didn't really get much time to sort of try to optimize the forest with whatever parameters there were. We picked, I guess, what, the 25% of a range of the
Hmm.
um classifiers, or sorry, estimators, but we couldn't match the Canon score.
Okay. Yeah, there are many ways to tune these things. We're going to learn some more ways next week. Um, it gets pretty interesting. Okay, Group 5, Armand, Mylan, um, Florina, and Natasha.
Yeah, I can go. So we also worked with the churn data. We found that we actually did use the reduction of the estimators for the random tree classifier, and it did give us a better result. It actually had the best result of all of the training models that we used, both in terms of testing and in training. Can't report any coding issues that we had working with this. It was actually pretty smooth after we got over that initial misunderstanding at the beginning. So, but it seems like random tree model worked the best for us at 64 estimators at 94.9 for the sorry 99.994 for the training data and 0.947 for the testing data,
Okay.
which was oddly similar across the board with yeah, never mind. It seemed like we had one that actually repeated the exact same scoring between yeah, K neighbors and random forest both got 0.949.
Interesting.
I thought that was interesting as well.
All right, so yeah. So you see people had a variety of different experiences, but with not a lot of practice, you're able to put a lot of different models together in a short amount of time and compare the results from many different models. Um, Towards that end, I want to show another tool that can be used when you want to like compare different models. And let me just show you that code. All right, so here I'm bringing in linear regression, train test split, blah blah, you know, stuff, and I'm also going to be defining a function, right? And so this function here, test model, I'm going to pass in the model and the data, right? And so it's going to do the works, right? It's going to say, okay, yeah, given the data and say X train scaled, X test scaled, Y train, Y test equals data. Now this assumes that data is coming in as a tuple of 4 values, and it's basically assigning those 4 values to these variables here. And then I'm going to say, hey, model.fit train scales Y train, right? That's going to give me the model, and I will get the model name by saying, hey, type the model and get the name, and then say reg.score, right? And score the model with the train data, and then score the model with the test data. All the things that we do separately, you know, is all wrapped up in this one function for now. So that can make life a little bit easier. So let's say I create some data, right? So I'm just going to say make regression. This is going to make some fake data. Make a data frame, do a train test split on it, set the scalar, and create the scale. So all of this will eventually say data equals, and then I got a list of all my data items. I'm sorry, it looks like it's a list, not a tuple. All right. And now I can bring in some models, right? I can say bring in k nearest neighbors, or k neighbors regressor, random forest regressor, extra trees regressor, ADA boost regressor, a whole bunch of new models, right? Even a support vector machine regressor. And now I can test them, right? So I pass in test model and I pass in the function and the data, right? Function data, function data, function data. And even for SVR, I can pass in some arguments, right? I can say, okay, give me an SVR with a C equals 1 and an epsilon of 0.2, whatever that means. And boom, right? I run the 6 models. I get the training and test scores for the 6 models. And we can see linear regression, 0.82, k neighbors regressor, 0.07, horrible. Random forest regressor, 0.24, horrible, right? Extra trees regressor, 0.44. You know, and we can see that for a lot of these, it's like really bad, but the linear regression is better. So just a way to like, you can test several models at once. So let's try this again. So I'm going to make a new set of data. And this is going to be make Swiss roll, which is a way to randomly generate data. It's kind of a funny name. It makes this roll, but we actually have a picture of it here. So put in the data frame, train test split, set the scalar, scale it, make my data. That's good. If I say X train scaled, you can say, okay, it's got that scaled attributes of it. We could actually plot it to get an idea of what we're dealing with. And it's going to be a 3D plot, projection equals 3D, and make it a scatter plot of feature 0, feature 1, and feature 2. And the color will be, you know, take the Y value and divide it by the max of the Y value. All right. And when we do that, we get this beautiful thing. So it's kind of a swirl in 3 dimensions, right? Like a jelly roll. And that's just creating test data so that we know what we're dealing with. And this test data, you know, Y, it's going to be like a multi-class Y. So good for linear regression, right? Since it's continuous. And then we can run test model using linear regression and the other several models and see how it does against this data set. All right, and here we're getting linear regression is horrible, right? Because this is not linear because it's, it's in a loop. But k-neighbors regressor does actually pretty well, 0.97, and Random Forest regressor and these other models do pretty well for this data. So here we find that several models are doing not too bad. Extra trees, 0.992, very, very well. So, the message here is like sometimes models perform badly on some data sets and then really good on other data sets. So there's no Swiss Army knife all-purpose model that works good for everything. And the other message here is that by automating things with a function, right, you can enable you to test several models very quickly and easily. So just a tool to keep in mind when you finally get around to getting to projects.
One question about the graph that you showed us, is there a method that we can view the plots from different angles? Is there a way to visualize it from different points of view?
Oh, probably. You could probably, this add subplot. It's view init, I think probably here, this view init, that's 7 and -80. I bet that controls some of the view angles of it.
Okay.
Let's try modifying those and see if it changes something. Like, let's change this to like a -40. Yeah, see that rotated it.
Oh, that is so cool.
All right.
A couple weeks ago, I shared a link in resources, it was for the k-means clustering, and the visualization was 3D and interactive. So you could look at that visualization as well. And then make this one interactive where you can drag it around and look at it from different angles.
That is very cool. Okay, I'll definitely be looking at that.
All right. Okay, so today we worked with multi-class data sets, and we looked at training multiple models and comparing how multiple models work together. Next week, we're going to learn how to fine-tune models as well as dealing with unbalanced data sets and looking at new ways to measure results beyond just accuracy. But that's it for tonight. Thanks, everybody. Office hours now open.
Thank you. Good night.